Welcome to Study Loop.
And so we are asked to consider a simple Brayton cycle between pressures of 100 and 1600 kilopascals. The working fluid is air. It enters at 40 degrees Celsius at 850 meters cubed per minute, and it leaves at 650 degrees Celsius. We're going to use variable specific heats for air and assume isentropic efficiency for the compressor of 85% and turbine isentropic efficiency of 88%. Our first order of business will be to find the net power output. Okay, so this will be 313 Kelvin, and this will be 923 Kelvin. Let's get those into Kelvin. We've got our efficiencies, and so R we're going to get from a table that will be 0.287 kilojoules per kilogram Kelvin, and our specific heat ratio will be equal to 1.4. So we need to interpolate between 2 points. So let's figure out here. So T in Kelvin, we've got 310 and 315. And our H in kilojoules per Kelvin per kilogram, and our S is in kilojoules per Kelvin or kilogram Kelvin. This will be 310.24, 315.27, 1.73498, 1.75106. So when we figure out where we need to be here, we're going to be using 313.26 kilojoules per kilogram and 1.744628 kilojoules per kilogram Kelvin. Okay, and now we can use the ideal gas law. We can calculate our specific volume. So let's rearrange. V1 will be equal R T1 over P1. So V1 will equal 0.287 times 313 times 100 kilopascals. And this will equal 0.8983 meters cubed per kilogram. And then we can find our mass flow rate. M will equal V1 over V1, and that will equal 14.167 meters cubed per second divided by 0.8983 meters cubed per kilogram. Hang on just a second here. And I want to go back here, my 850. This is my 14.167 meters cubed per second. So I just divide that by 60. Okay. Okay, let's see here. And this will equal 15.771 kilograms per second. Then at point 4, we've got 920 and 940, and our H4 here will be 958.761 kilojoules per kilogram after interpolation. So between points 1 and 2, we have an isoentropic process. So the temperature at point 2s we can find by using the fact entropy change is 0. Okay, so S, and that will equal delta S, and that will equal 0. And that gives me okay, so S2 for 1.74428. We calculated that on our previous page. I'm going to take that plus R times ln of 1600 over 100. And this will give me my S20 is equal to 2.54061 kilojoules per kilogram Kelvin. And then we can find our entropy at 2S. We're going to look at our table again. And that will give us 690.88. So then we'll know that our work input would be equal to H2S minus H1. That'll equal 690.88 minus 313.26. Both of these are kilojoules per kilogram. And this will equal 377.62 kilojoules per kilogram. So then we can find our isoentropic compressor. We're going to find the work input for our cycle. So solving for work in, we'll have work in for our reversible over this. And this will equal 377.62 kilojoules per kilogram divided by 0.85, and this will equal 444.259 kilojoules per kilogram. Then at point 2, I'm going to switch colors here. We're going to get the energy balance by W in will equal H2 minus H1. So H2 will equal W in plus H1. This will equal 444.259 plus 316.26 kilojoules per kilogram. This will equal 757.519 kilojoules per kilogram. Okay, and then to find H2, we're going to know that T3 is higher than T2 and T4. So we're going to assume some temperature and then keep changing it. So this wasn't my favorite thing here. Let me jot down and that will equal H3 minus H4 over H3 minus H4S. So H4 will equal H3 minus, whoops, okay, so we found a value for a few temperatures here. Let me write a couple down here. These are all in kilojoules per, well, they're not all. This is in kilojoules per kilogram. My H's are in kilojoules per kilogram. And these two are kilojoules, whoops, kilojoules per kilogram Kelvin. Okay, so let's write these down. Okay, I'm just writing as fast as I can here. Okay, eight zero eight 2.74306. Here you have 817.752.927.602. Almost done with this part. What did I write there? That should have been 854. And then there we go. The closest value we get will be 1620. So H3 will be 1782. And then we can find all of the asked for volumes. A. The net power output. There we're at 823. 0.239, so that the net, this times W out minus W in. So this will equal 15.771 times 823.239 minus, that was 444.259. So my work net will equal 559.76.9 kilowatts. B, asks us to find back work ratio. And that will be this will be 444.259 divided by 823.239. This will equal 0.54. Okay. Then next, C, asks us to find thermal efficiency. Okay, thermal efficiency. This should be my hardest part here. So this will equal 15771 times minus, and this will give me my Q in of 16157.1 kilowatts. Then our thermal efficiency will this be our net divided by our Q in, and this will equal 5976.894 kilowatts divided by 16157.09 kilowatts, and this will equal 0.37. Okay, and I just want to run through a couple other things quick here. Okay, that should be good.